Hello everyone. Hey guys, this is your J educator Megha, and guys, I'm going to teach you organic chemistry. So there are the very basic concepts of organic chemistry. If we are good in that, then only we will be able to focus more on the reaction part and the reaction mechanism. But if the very basics of the topic of organic chemistry, like the electronic displacement methods, okay, if we are not good in this particular thing, then we always find it difficult to solve questions, okay, that comes in your JEE mains or advanced paper. So today, through this session, I will be making this thing very easy for you. All the 4 electronic displacement method, as the topic says, electronic displacement means we have to displace the electrons. So what are the methods to displace those electrons? Okay, the bonded electrons. Okay, so the 4 methods, inductive, electromeric, resonance and hyperconjugation, will be discussed in class. So if everything is good, you are all able to understand that the slides is visible and I am audible, then please do let me know so that we can proceed with the session. So guys, you please give a thumbs up if everything goes well. I can see Vardman is there, Kaushal is there, yeah, and who else? Okay, so whosoever is joining me live for the class, please guys say hi and audible and visible. Okay, yeah. So this is the assurance that I want from your side. Thank you so much. So let's proceed. All the 4 methods will be discussed with you in a very simple and lucid way. So the very first method that we are going to study is the inductive method. Okay, so what is this inductive? Okay, so first of all, let me tell you what is this. As I told you that this is an electronic displacement method. Electronic displacement means we have to displace the electron. So how there will be a displacement of electron? Electronic displacement. Okay, electronic displacement method. I can simply write method. Okay, so if I take a bonded pair of electron, let me take an example. If I take a bonded pair of electron, I take CH3, CH2, OH. Okay, so this is my molecule. I want to draw this kind of structure, that is carbon, hydrogen, hydrogen, hydrogen. Okay, this is again a carbon with the 2 more hydrogens, and this is the oxygen and this is the hydrogen. Okay, so we have to think for the displacement of electron of a sigma bonded electron. So inductive effect says that you have to displace the sigma bonded electron. Now the question comes ki, okay, we have so many sigma bonded electron, they are also sigma bonded. So what type of displacement we have to do? They all are sigma bonded electrons, right? So which electrons will get displaced? Which electrons will get displaced? Guys, only those electrons can get displaced where there is a polarity. Only the displacement of that sigma bonded electron can happen where there is a polarity. Where there is a polarity. Now what do you understand by polarity? Polarity, the another term that I can use for polarity is, that is the electronegativity difference. Electronegativity difference. Okay, now again let me tell you about it. So this is the displacement of sigma bonded electron. So we have so many sigma bonded electron. Now we want to see that who will displace and who will not displace. Guys, if you will see this question, carbon and hydrogen are very similar in their electronegativities. Carbon electronegativity is 2.5 and the hydrogen is 2.1. Okay, so not much difference. So why there would be the pushing or pulling of electron? Okay, this is 2.5, this is 2.5. Of course, they have the same electronegativity. There will not be any displacement. Carbon and oxygen. Carbon is 2.5 and the oxygen is 3.5. Okay, yeah, we can see that oxygen and carbon are having a much difference in their electronegativities. 2.5 and 3.5. Now, just wait. If I look for the hydrogen electronegativity is 2.1. That is 2.1. Okay, So first of all, what we can see, where we are having the electronic displacement, where where we have the highest polarity. Okay, so guys, if you would see, the highest polarity is basically between the O and H bond. Okay, they are highly electronegativity difference. One is 2.1 and another is 3.5. So much difference as compared to that of the carbon and oxygen. Now, so where we have to see, basically, we have the organic compounds. Organic compounds are the compounds which have a carbon containing compounds. So all the part of the carbon is basically part of an organic compound. Okay, but here we have an heteroatom. So if you will see this carbon part, and if you will see this particular group, that is the OH group, so we have to see the electronegativity difference between the carbon part and the group. So this is your carbon part, this is a carbon family. So this is my carbon family. So this carbon family needs to know that what this group is going to affect. Okay, how is this group is going to affect. So if you will see 2.5 and 3.5, we can see that this OH is highly electronegative. So ultimately what will happen? There, this pair of electron will get displaced in this particular direction. So between the carbon family and the group, we have to see the sigma bonded electron will get displaced. Where? So because oxygen is more electronegative, and electronegativity means the pulling of shared pair of electron towards itself. So ultimately we can say that the bond will not be broken. Only the displacement of electron will occur. Now you would see ki here, if you are having such kind of molecule, we can show that the pair of electron is present more close to the oxygen. So there is a displacement of electron towards oxygen. Okay, here the pair of electron is more close to the oxygen, and this is it. Okay, so this is what the inductive effect is. That is the displacement of sigma bonded electron. Now if this group, now if this is a group which I am talking about, if this group is pulling the electron towards itself, then if a group pulls the electron towards itself, pulls the electron pair towards itself, it is known as electron withdrawing in nature. It is electron withdrawing in nature. Electron withdrawing in nature. Okay, but if we have any such group, electron withdrawing in nature, so this is also known as, it is represented as minus I effect. Okay, this means that here the electrons are pulling in nature. So I can show you here, if you are looking for the minus I effect group, so any of the group like O positive, Nr3 positive, NO2, Cn, so whosoever when attached with the carbon family, let's say here I am having a carbon and here I am having a O positive. So now O being electronegative and having a very positive charge will try to pull the electron pair from the carbon towards itself. So ultimately, who? The carbon and the group. So we have to compare between the carbon family and the group. So if a group is electron pulling in nature, it will be considered to be as the minus I effect. Okay, now let me tell you what about the electron releasing in nature. Okay, so let me give you one more example here. Okay, just a minute. Okay, so this is the example 1. Now I will be taking an example 2. Now see, we have so many groups which are also plus I in nature. So how they are going to be plus I in nature? Okay, so let's have a look. Sorry, let's come over this side. Guys, now we can see that if we are having a carbon family, okay, this is my carbon family, and here I am having O negative, okay. So you just think that. So this is the carbon family with carbon hydrogen bonded pair of electrons. So this is my carbon family, and I have to compare this with this group. So if I focus over there, you will say that ma'am, here carbon and oxygen is very electronegative. So if I am looking for for this pair of electron, then what you would see ki yes, oxygen is more electronegative. But guys, just focus over one of the most important thing that we should okay, which cannot be avoided. That is, here we have oxygen is negative charge. So oxygen is already electron rich in nature. It does not require electron, because if an oxygen which is highly electronegative also bearing a negative charge will pull the electron, there will be instability, because excessive of anything leads to instability. So reason being, how there would be a polarity. Now this oxygen don't want to pull the electron. The oxygen wants to neutralize its electron pair. So guys, please write down a thumb rule. Please write down a thumb rule. Thumb rule is, neutralization is stability. Neutralization leads to stability. Okay, and if you are doing excessive of anything, excessive of charge leads to instability. If there will be an excessive of charge, so now you think, if this oxygen will pull the electron pair towards itself, then there we will be having an excessive of charge. O will be bearing more negative charge. So no, that will lead to instability. So because of that reason, oxygen will not pull the electron towards itself, but the opposite of this will occur. That is what we can see, that here from this carbon family we will be having CH, and here this bonded pair of electron will go towards carbon. So basically oxygen don't want to pull the electron, the oxygen wants to push its electron pair. So whenever there is a pushing of electron pair, not pulling, okay, so what this group is doing, the group is giving its electron pair. Okay, so whenever, if a group give its electron pair, matlab donates electron, if a group donates electron, then it is said to be electron rich, or yani ki we can say that it is electron donating, electron rich or electron donating in nature, electron donating, and sometimes we also say electron releasing in nature, I hope it's clearly visible to all of you. Okay, and it is represented as a plus I effector. So I hope you got the difference. Inductive effect is very simply the displacement of sigma bonded electron. So which sigma? The sigma between the carbon family and the group, Now we have to focus over the group, that what type of group we have. If any of the group is having a tendency, this was neutral. Okay, so being an electronegative atom, it was having a tendency to pull the shared pair of electron towards itself. So that's why this was minus I. This was showing the minus I effector. Okay, but here we can see that being electron rich in nature, it doesn't want to pull the electron because the excessive charge leads to instability. So rather than that, it will try to push the electron pair. So if there will be a pushing of electron, if the electron pair goes more towards carbon, then it is known as the electron donating or electron releasing. That is, we can say that this is showing the plus I effector. Okay, and guys, this type of displacement of sigma bonded electron is basically a permanent method. Okay, so the displacement of electron occurs permanently. It's a permanent method. Clear? Now we can see that over the carbon family we can put many groups and we can apply the same concept. Okay, now let me tell you, if you will compare between the Nr3 and if you will compare the NO2, why the Nr3 is having more minus I effect than as compared to that of the NO2. Let me talk about this particular thing. Now guys, let's take an example. Okay, you need not to learn this whole table. It's very simple. If I put N, this is your R3, and here I am having a positive charge. And I am having another example where we have a carbon, and this is your N, double bond O, and this is your O. Now you have to compare, where you have to see what happens in this particular bond, right? If you would see guys, here we have a nitrogen which is an electronegative atom, but see, there we have a positive charge. So, and here the nitrogen is neutral. Okay, so first of all, look for the atom with which the carbon is directly attached. So if you will see, this is CN bond, this is also CN bond. But what is the difference between the two CN bonds? Here over the nitrogen we have a positive charge. So of course I told you, positive yani ki neutralization leads to stability. So nitrogen being a positive wants to neutralize itself. So because this nitrogen wants to neutralize itself, it will pull the electron pair towards itself. So ultimately here we will be having the displacement of electron towards nitrogen, so that at least it gets stable. Okay, I'm not saying that the bond will be broken, the bond will remain as it is. It is a covalent bond. Okay, we can't break the bond, but yeah, there will be a displacement of electron. The electron will try to go more close to nitrogen, so that it becomes neutralized. Okay, and hence leads to more stability. Okay, so ultimately here what type of effect this group has shown? This group has shown pulling of electron, that is minus I effect. Okay, this has shown minus I effect. But now if you will see this nitrogen, all of course this carbon and this nitrogen being more electronegative as compared to the carbon, nitrogen is 3.0 in its electronegativity. Of course there will also be the pulling of electron. Ultimately we can see that here also there will be the pulling of electron. But if you will ask me that which is more minus I in nature, this is also showing the minus I effect. But if you ask me which is showing the more minus I effect compared to that of the carbon, then definitely the answer is this. Why? Because here we have nitrogen as positive and here we have nitrogen as neutral. So the positive ones will pull the electron more strongly rather than the neutral one. Now if you would see, ma'am, this is O positive and this is N positive, then why O positive is more pulling in nature? Because guys, relatively if you will see, oxygen is more electronegative rather than nitrogen. So a being more electronegative atom, this wants to neutralize first. Okay, so more the electronegativity, the positive charge is not at all stable. An electronegative atom can only bear a negative charge, not a positive charge. So that's why this is strongly pulling in nature. Okay, then comes Nr3, then comes NO2. Okay, this is N positive and this is N neutral. If you would compare cyanide, so here we have a carbon with a triple bond N. So yeah, yes guys, here if we have a carbon, this is a, let's say this is a carbon chain, and we have to compare between this and this. So this is a carbon which is sp hybridized. So here the percentage of S character is very high, because of which it is more electronegative, even more electronegative than that of the nitrogen. Yeah, this carbon is even more electronegative as compared to that of the nitrogen. So that's why here this will try to pull the electron rather than comparing with the C double bond O. Okay, because if you will talk about the carbonyl, we simply have C double bond O, which is sp2 hybridized, not sp hybridized. Here we have a C double bond O, and then we will be having a C triple bond O. We can say that because there we will be having a back bonding. Okay, this kind of carbonyl group. Then after comes your fluorine, absolutely. Then comes your COOH, then Cl, then Br, then I, then OH, then NH2. NH2 is basically, this is more electronegative oxygen, so it's more pulling in nature, and the light nitrogen is less electronegative, so it is not that much pulling in nature. So whosoever, as the electronegativity increases, we can say that as the electronegativity increases, the electron pulling property increases. Okay, so as the electronegativity increases, so let me compile this inductive effect in just simple words. It is simply a displacement of sigma bonded electron. It is a permanent displacement method. Okay, you can relate it this with tug of war. Okay, in the tug of war, you might know about this game. If there is a rope and if there is a pushing or pulling of the rope. Okay, so whichever the team wins, that will be considered as minus I, and whosoever the team loses will be considered as plus I. Okay, so you can relate this with the game tug of war. And the last but not the least, inductive effect, okay, is simply can be seen in the carbon containing compounds, or you can relate it with the polarity. How you can relate it with polarity? You just have to relate it with polarity. Means you just have to see where there is a polarity, where there is a positive negative charge. That's it. So guys, with this, now let's move on to the next method, that is the electromeric effect. I can see many of you are already watching. How is Namaste ma'am, positive and negative character? Absolutely. Okay. Should we learn the electronegativity values for frequent elements in organic chemistry? You at least need to know the Pauling's electronegativity values. Okay, because it is given for the period number 2 and period number 3 elements, so you respond in a better way whenever there will be a question. Clear? Caution? Okay, so guys, this is my request. If you're finding any difficulty or if you want to know any other thing, please do let me know just by a comment section. Okay, and if you are done, if you understood the inductive effect, then please give a like, so that I get to know that yeah, this topic is like much more stronger. And then after teaching you everything, I am going to give you a comparison. Okay, that is what happens in the inductive, what happens in the electromeric resonance and hyperconjugation. So at least for once, let me give you a clear idea that what happens them separately. So here the electromeric effect. Electromeric effect is simply the displacement of pi bonded electron. This means that yes, of course, here we are going to do the displacement, but of sigma bond electron, no, this is a displacement of pi bonded electron. So let me take an example, guys. Here if you would say, ma'am, in this question will there be any electromeric effect work? No electromeric effect. No electromeric effect. Why? Because there is no pi bond. There is no pi bond. Okay, now if you ask me, ma'am, will there be any electromeric effect now? Yes, absolutely. There we will be having the electromeric effect. Yes, the electromeric effect. For the electromeric effect, what is the compulsion? If for the electromeric effect, there must be a pi bonded electron. Okay, if you ask me, okay, ma'am, do we have the electromeric effect in this particular question? Yes, we could have the electromeric effect because here we have a pi bond, right? Okay, we do have the electromeric effect in this particular question. Yes, because here wherever you will be having a pi bond, there we can see the electromeric effect. Okay, there we can see the electromeric effect. Now what do you mean by the electromeric effect? For the electromeric effect, the pi bond is compulsion. Now the displacement of pi bond. So basically what happens, guys, as and when there will be a presence of any unsymmetrical reagent. Let's say I have taken A and B, which is an unsymmetrical reagent. Either you take any unsymmetrical reagent or you take any kind of ion, okay? Or I can say I have taken A positive or I have taken B negative, or in the presence of any ion. Okay, what happens is there will be a displacement of this pi bonded electron will displace either on this side, either on that side. Okay, whenever there is a presence, only and only in the presence of an unsymmetrical reagent. Okay, so ultimately here what will happen? We can see that this will result into the formation of RCH2 single bond CH2. This will become negative and this will become positive. So ultimately what has happened? There is a displacement of pi bonded electron. Are you getting? Now here we have this as a pi bonded electron. So again, in the presence of any unsymmetrical reagent, when this pi bond gets displaced, just like that, RCH2 CO. Now you tell me where this bonded pair of electron will get shifted. Guys, oxygen being an electronegative atom, definitely this will try to pull the electron. So this will become negative and this will become positive when in the presence of any unsymmetrical reagent. So unsymmetrical reagent is the necessity for the electromeric effect to occur. Now here if you would see in this question where we have a pi bond, we have a pi bond here. So ultimately this pi bonded electron will get displaced in this particular direction. Okay, ultimately again in the presence of any unsymmetrical reagent or cation or anion. Okay, so ultimately what results into the formation of CH2C double bond N, this will become negative or this will become positive. Are you getting my point? So electromeric effect is the displacement of a okay, so that will be the displacement of pi bonded electron. Now this is also a tug of war, but the tug of war is between a pi bonded electron. Now guys, this is the most important thing that we need to know is there also we need to know about the polarity. Polarity, that is the electronegativity difference, of course. So whenever there must be an electronegative atom, the cleavage of bond will be in that particular direction. If O is more electronegative, the negative will come over oxygen, and over the carbon we will be having a positive charge. Polarity, that is the electronegativity difference, we have to focus. There is one more thing that we have to focus is this electromeric effect is a temporary displacement method. temporary displacement method, means this is a temporary method. So what do you mean by that? Guys, this simply means that if there is an unsymmetrical reagent, this bond cleavage will occur, otherwise it will remain as it is. Only in the presence of unsymmetrical reagent the reaction will go forward, otherwise there will be no cleavage. Okay, so that's why we are saying that this is a temporary method. Okay, simple, that's it. Now we have the another. Ma'am, when I revise some points looks like alien. Why so? Okay, Kaushal. It keeps shifting. Okay, so understood. Very easy. So we will be trying to compare all the methods all collectively. Okay, as I told you. Now the resonance. What do you mean by the resonance? Is the resonance is a displacement? That is a tug of war? No, no, no. Resonance is basically a delocalization. Delocalization. Here again we are talking about the pi electron, but we are talking about the delocalization. So what do you mean by that? Now guys, in the case of the inductive effect, in the case of the temporary effect, we just were looking for the 2 atoms. But now here in the case of resonance, we will be looking for the 3 atoms. Absolutely. Okay, 3 atoms. So what are those 3 atoms? If here, let me take a question like we have CH3, CH2 and CH3, CH2OH. Let me take an example like CH3, CH2, CH2, double bond, CH2. If I take an example like CH3, CH, double bond, CH, CH and OH. Okay, so there we have the 3 examples. Okay, so what is the difference between all the 3 examples? Guys, if you would see, there we have only sigma electron. So in the case of the sigma electron, yeah, the inductive effect could take place, right? So here this group will show the inductive effect, right? Here if you have a pi bond, so pi bond can be displaced in whichever the direction, so the displacement of pi bonded electron will take place. That is, here the electromeric can happen. Electromeric can happen. But what can happen in this case? Here we have a pi bonded electron, but at the same time we are also having one more thing. What is that? What is that? Here we are also having one more thing, that is the lone pair of electron over the oxygen. Yes. So here also we have a pi bond, but the difference is there we have a oxygen as well. So now guys, here in the case of the electromeric effect, your focus was only on the 2 atoms, that is X and Y. But now here in the case of the resonance, here I will be telling you the concept of resonance. Your focus has to be over the 3 atoms, X, this is Y and this is Z. So here we have X, double bonded Y, single bonded Z. So let me tell you, yes, inductive may also you were focusing over the 2 atoms, only the carbon and the oxygen. Here also you were focusing over the 2 atoms only, X and Y. But here in the case of resonance, you have to focus over the 3 atoms, that is X, Y and Z. Okay, so what does this mean? So whenever guys you will be having, so what is the condition for resonance? Let me tell you. What is the condition for resonance? Condition for resonance to occur. So whenever you have any X, double bond Y, single bond Z, and over that Z whenever you have a lone pair, X, double bond Y, single bond Z, or whenever you will be having a positive charge over the Z, X, double bond Y, single bond Z, you have a negative charge over the Z, X, double bond Y, single bond Z, whenever you have a pi bond over a Z. So X, double bond Y, single bond Z, whenever you have any kind of vacant orbital over the Z, or even you could have any radical over the Z. So whenever you have all such conditions, there would be a possibility of resonance. There would be a possibility of resonance. Are you getting? So these are the conditions for resonance. So whenever you get a pi bond, okay, and along with the pi bond, if over the Z point, I'm not saying this has Z. Why? I could take this X, double bond Y, Z, but over the Z I am not finding any such thing. So there is no possibility of resonance. So that's how I avoided that. Okay, I will try to find out a system like which I have mentioned you all there. Okay, so when I will be focusing over this kind of system, I will get to know, okay, whenever we will be having such kind of system, x, y, z, z is having a lone pair, and the z has to be uh, Z has to be of any atom. Okay, this could be carbon, this could be nitrogen, this could be oxygen, this could be any atom. Okay, X and Y could be any atom. Okay, so only this system we are looking for. Then ultimately what will happen? We will be having a delocalization of electron. Delocalization of a pi bonded electron. Pi bonded electron. Now you see, this is a pi bonded electron. Now we have to see that where there will be a delocalization. So oxygen, a lone pair which is free, which is easy to be given. So this oxygen will try to give its electron pair to this carbon, and this bonded pair of electron will be broken in this particular direction. Ultimately we will be getting a resonance, and for the resonance we put a double-headed arrow. Okay, this means that resonance basically tells us the two non-real structures. So ultimately the structure number this first and the structure number 2 that I will be drawing, they are the non-real structures. The actual real structure will be lying in between the two. Okay, means whatever we will be writing, they are going to be the non-real structures, and the real structure lies in between the two. So the second structure is going to be CH3 CH. Here we will be getting a negative charge. The bond will be broken in such a way, CH double bond O, O positive, and this is going to be the H. So yes, if you ask me, structure number 1 and structure number 2, they both are the resonating structures, but these are the non-real structures. Okay, but the real structure lies in between the two. That's why we are saying that it's a double-headed arrow. It is in between the two. Okay, and if you ask me, out of these two, 1 and 2, which is more stable, of course 1 is more stable than the 2, because in the 1 the octet is complete, and other than octet it's a neutral with complete octet. So why the 1 is more stable? Because it's a neutral structure with complete octet. I am not able to write it here, with complete octet. Okay, with complete octet. So that's the reason for it. Okay, ultimately now let me tell you that what kind of resonance can occur. Guys, here we have to focus over this Z, that what type of group is this, whether it is pulling the electron or whether it is giving the electron. Okay, if this Z is electron giving in nature, okay, so what type of Z is this? When the Z is giving its electron pair, okay, then it is said to be plus R. That is it is activating the group. It is giving its electron. So this will be showing the plus R effect. So ultimately how this would be written as X negative, single bond Y, double bond Z, and over the Z we will be getting positive. So this will be showing a plus R effect. So we have to identify the nature of this Z. Okay, now if I ask you that what type of nature of this Z is, so ultimately guys, here we can see that this is positive. So positive means deficiency of electron. So this will try to ask for the electron pair. This will ask, okay, pi bond, you please be broken and give me the electron pair. Okay, so here we will be having a delocalization of pi electron in the direction of Z, that is towards Z. If there is a delocalization towards Z, it is said to be minus R in nature. Minus R, it has electron pulling behavior. Okay, so ultimately we can show it like X, Y, double bond Z, and here we will be getting a positive charge, and this positive charge will get neutralized. Simple, this would be the structure. Now for the third, if you will ask me what type of Z is this, guys, it is already negative, so it does not want more electron. It wants to neutralize itself. Neutralization is the thumb rule. So this Z will try to give the electron pair towards this X. Ultimately what will happen? If this is giving the electron pair, then it is said to be plus R in nature. This will be plus R in nature. Ultimately, we can say that this is X, Y, double bond Z, and here a negative charge will be there. Okay, and this negative charge will get delocalized. Okay, so this is the delocalization of electron with a pi bonded electron. Delocalization of pi bonded electron. Now ultimately, if in the next case we will be focusing, so here this is also a pi bond and this is also a pi bond. So they are like in nature. So here we have to focus, okay, so whatever be the atom bonded with this Z, How it is? Let's say if it is an oxygen being an electronegative atom. So here the nature of the atom is going to decide where there will be a pushing or pulling of electron. Okay, now if the nature of the atom is kind of oxygen which is strongly electronegative, then definitely it is showing minus R effector. Minus R effector. So I can say that this is X, Y, double bond, Z, Z, and here we will be having O. So now whenever there will be this kind of delocalization of pi electron over the X, there is a deficiency, we will be putting positive charge. This is a double bond. Over the oxygen we will be getting a negative charge. Now again, if I look for this particular Z, how it is behaving, guys, this Z is vacant in nature. This is saying that I am having a deficiency of electron. So if it is having a deficiency of electron, definitely it will try to pull the electron pair. So ultimately we will be getting X, Y, double bond, Z, and here we will be getting a positive charge because of the deficiency. Okay, it doesn't mean that we will show a vacant orbital. We can only show it this with a charger. Okay, we can't say that the vacant orbital will be there or lone pair will be there. The lone pair is delocalizing, but we can only show it with the help of the charge, that is either positive or negative. Okay, so this is it. So ultimately how it is behaving, this is also minus R. Minus R. This is also showing the minus R effect. I hope this is visible to all of you. This is showing the minus R effect. Now here if we are having a radical, you know radicals are also the 7 electron species. They are also deficient in nature. Okay, so because of the deficiency it is also looking for the electron. So ultimately whenever, but in the case of a radical, because it's a single bonded pair of electron, so here we will be getting a radical. This is Y, double bond Z, and here the electron deficiency will get completed. So this is also minus R in nature. Okay, so this is the way, by the direction of the electron displacement method. You know, all these displacement methods are direction dependent. We have to focus over their direction, in which direction they are moving. Okay, so if any of the group, if here I am talking about which group, here I am talking about the group, here I am talking about the group that is Z. Okay, I am talking about the group Z, that how this Z is behaving. So this is it. Okay, understood, Rohit? If you have any doubt, please do let me know. Is everything fine? You all understood what is resonance? So now what type of resonance is? Resonance is also a, now let's talk about few points. Guys, we can say that in the case of resonance, there is a delocalization of pi electron. So until unless you will be having that particular system XYZ, 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 there will be the delocalization which will keep on going, keep on going, keep on going. Okay, so this delocalization will keep on going. Okay, so you can relate that delocalization of electron, that is I am giving to someone, someone is giving to the another person is giving to the another person. So this is a kind of a passing the flow game. Okay, so we can say that it's a kind of a passing the flow. So what I can say that it's a kind of, we can relate it with a passing the flow. Passing the flow. Okay, we can relate it with the passing the flow. So are you getting the difference between the inductive, electromeric and resonance? In the case of inductive, we were having only sigma bonded electron, and we have to figure out that which particular group is affecting. Okay, so this is my carbon family and this is a group. So we have to see that what type of effect this is showing. So here the pulling of this particular electron pair will occur. That is the displacement of sigma bonded electron. In the case of electromeric, I talked about the displacement of pi bonded electron. So here we were having a pi bonded electron, so we were looking at where it is getting displaced. Okay, now in the case of resonance, we were saying, okay, we have a pi bonded electron, we have a pi bonded, but now we are talking about the delocalization, not the displacement. Difference is there. Delocalization, okay, delocalization of this pi bonded electron, and for that this lone pair or a positive, negative pi bond or a vacant orbital is very, very necessary. If this system is there, then only the resonance will occur, otherwise the resonance will not occur. Okay, now guys, here I can show you there are many groups which can show the minus I or minus M, or the difference between the vacant orbital and a positive charge on an atom. Okay, positive charge means that it's a cationic species where there is a loss of electron, and because of the loss of electron it is deficient. But a vacant orbital means you are having a such kind of element, जैसे कि as you can say AlCl3. AlCl3, aluminium has bonded with the 3 chlorine, but still one of the vacant orbital is there. You can say that in the case of SO2 we have a vacant d orbital. So because of that vacant orbital, this can have a tendency to pull the electron. Okay, because sulfur can expand its octet. That's the point. Okay, Kaushal, got it? Okay, so deficiency could be because of the extra empty orbital present, or because of the there is a positive charge, there is a loss of electron, and so therefore any of the species has become deficient in nature. Okay, so this is the point. Now guys, we can see that O positive, why this O positive is pulling the electron. Now let me take a few examples and we'll tell you again. So here I have taken, there must be a possibility of a pi bond first. The pi bond is very very compulsory. X, double bond, Y, single bond, Z. And over the Z, a lone pair, a positive charge, a negative charge, or a pi bond, or a lone or a radical, or a vacant orbital. Vacant P or either vacant D. Any vacant orbital could be there. So here if I take an example, like CH2 double bond CH single bond O positive, I can see that we have a system. This is X double bond Y single bond Z. Z pe we have a positive charge, so we can say that O positive, because positive has a deficiency, and we know that neutralization means stability. So oxygen wants to pull the electron to become more stable. So it will try to pull the electron. Ultimately the resonating structure comes out to be CH2 CH double bond O, and here we will be getting a positive charge now. So this is its resonating structure. Okay, and if you would see, these are two the resonating structures of each other. Now if someone asks you, this is a Z group, so what type of effect this is showing? So this is pulling the shared pair of electron towards itself. Okay, that is a delocalizing the shared pair of electron towards itself. So this is minus R in nature. Okay, you know, in our house we could have two type of guests. Some guests brings present to us. Okay, they brings gifts for us, so we always like them. But there might be some guests, those who always come and take gifts from us. Okay, so we really don't like them. Okay, so this is simple. So whosoever brings some things to you, whether chocolates or something, candies or whatever you like, so you find them positive in nature. You get the positive vibes from them, and you keep liking them. So this is it. So whenever any atom, whenever any Z atom comes and brings something to the carbon family becomes very happy. This shows that that particular Z atom is positive in nature. But here we were having such kind of Z atom who is such kind of guest, who is coming to our house, but is trying to get the things from us. Okay, so we really don't like that person. That's why we have a negative impression from that person. That's why this is negative in nature. Okay, so this is how you could be able to relate it. Okay, got it, Kaushal? No, this is not tautomerism. Absolutely not. In the tautomerism, guys, if you're getting confused with the tautomerism, then let me tell you, in the tautomerism you will be having a system X double bond Y single bond Z, but over the Z you will be having hydrogen. See the difference. Here also you are having XYZ, here also you are having XYZ, but here we could be having the electrons ka case, that is lone pair, positive, negative, pi bond, radical, vacant orbital. But here you will be having the hydrogen, which has to be acidic. If you have this kind of system, then this is known as tautomerism. Understood? Memir, okay, the difference between the tautomerism and the resonance. Okay, so here in the case of tautomerism, the sigma bonded electron gets displaced. Okay, and here the resonance sign is this double-headed arrow, and for the tautomerism we write this kind of sign, which is an equilibrium. Okay, this shows that the hydrogen will come over this H, and this electron pair will go to this. So ultimately I can say that XH single bond Y double bond Z. So these are the two tautomeric structures of each other. Okay, so this kind of displacement of hydrogen will occur. So here we have hydrogen, but here we have electrons. Okay, so I hope you got it. Now if you would ask me, ma'am, how this NO2 shows a tautomerism, shows the resonance, let's have a look over the example. I can take the example as CH2 double bond, CH single bond, CH single bond, or what I can do. Let me correct the question, just a minute. Okay, so I can have NO2. So when you will see this NO2, you will find that, oh, there is no resonance or there is nothing. But just guys, try to open the structure. What is the structure of NO2? Just try to open it. It is NO2. NO2. So now if you would see, you will be able to do the question very easily. Now you can see that this is X, this is double bond Y, single bond Z, and over the Z we have a pi bond. Okay, now if this pi bond is visible to us, we know that, okay, this is a resonating system. If this is a resonating system, we have to see where the pi bond will get delocalized. Okay, so here we can see that N and O, oxygen is more electronegative. This will try to pull the electron here as per the electromeric effect. Then definitely this pi bonded electron has to move in this particular direction. Now what type of guest is this? If I ask you, NO2 is coming to your house, so what type of group is this NO2? NO2 is bringing something to your house? No, this is such kind of guest who is taking the electrons from us, who is taking the chocolates from us. So we would say that this NO2 is minus R in nature. Okay, so the resonating structure for the question is going to be CH2. Here we will be getting a positive, CH double bond N, O negative, and this is going to be the same. Okay, so this is the resonating effect. Okay, so it could be a plus M, it could be a minus M, or guys, we can say that minus R or minus M is the same thing. Similarly, plus R or plus M is the same thing. Okay, so need not to confuse between the plus R and plus M, and minus R and minus M, because the resonance effect can also said to be the mesomeric effect. So when we say that this resonance is a mesomeric in nature, we use minus M. Okay, okay, chalo. So here we will be moving ahead with the very last electronic displacement method, which is the hyperconjugation. Now guys, in the hyperconjugation, we are again having the delocalization. But of what? Here we are having a delocalization of sigma electron. Delocalization of sigma electron means we will be having a delocalization. Yes, we will be having delocalization, but sigma electron. What does this mean? Okay, this is also known as the single bond resonance, because here we are talking about the sigma electron. So this is also known as the single bond resonance or no bond resonance. Single bond resonance. Okay, or no bond resonance also we say sometimes. Let me take an example and then I would be helping you. So let's say here I'm having a C positive, and this is a carbon, this is a carbon, this is a hydrogen, and this is again the carbon, again the carbon, and again the carbon. So when you will see this particular structure, what you can see? You can see that there is a positive charge. So if something is asking for electron, something wants to neutralize, something is looking for the electron. But who is going to help this particular carbon with a positive charge? So this carbon with a positive charge is saying, oh, please send someone who can make me stable. I want electrons. So who would go to stabilize this carbon? Now here we can see that, is there any electronegativity difference? No, this is a carbon, this is a carbon. Okay, so whenever we have such kind of species, we would be looking for what we would be looking for. We will be looking for the X and Y positions. Again, we have what type of positions we have? We have X and Y positions. Only two atoms we have to see. Okay, and this Y atom is actually known as the alpha position. Okay, means the carbon, I will be looking for the help from the nearest person whosoever to me. Okay, so if I get any emergency, okay, so who is going to help me? the one who is sitting very very far away in another country, whosoever is there, whether it's about my mom or my brother who is staying very very far away in another state, another country, is going to help me? No. So whenever I will be getting into any emergency situation, only the one who is more close to me is going to help me, whether it's my neighbor, whether it's my the person who is just besides me, can only help me. Okay, so here I want to tell you guys, if this carbon is having positive, so who is going to help this carbon? The carbon which is just next to this carbocation, or this particular carbon? No, this particular carbon is not going to do anything because it's not the nearest one. The nearest one is this, and the nearest one is this. Okay, the closest one is going to help. Okay, so whenever there is an emergency, only the nearest ones can only help you. So neighboring ones, so this is a neighboring rule. Okay, you can say that it's a neighboring rule, and these neighboring carbons are known as the alpha carbons. Okay, so now let's see what will happen. Guys, here as I said, we will just be focusing over the two atoms, that is the one with the alpha carbons. You can say that this is alpha. So here when we have any alpha hydrogen, that can only help you. So these are the alpha hydrogens. This is also the alpha hydrogen, means the hydrogen attached to the alpha carbon. Is there any alpha hydrogen? This is my alpha carbon, but do we have any hydrogen attached to it? No. So only the alpha hydrogen undergoing resonance. Okay, so now let me tell you again. I am writing the structure again. This is the CH3. This is carbon with CH3. This is with again CH3. This is a carbon with positive charge. This is a carbon with the 3 hydrogens. Okay. So if I look for any help over this particular alpha, then it is not going to help me because it has no alpha hydrogen. This alpha carbon has no alpha hydrogen. Okay, that is the hydrogen attached to this carbon directly. If I look for this particular alpha, yes, this has 3 alpha hydrogens. Okay, this alpha carbon has 3 alpha hydrogens. Okay, so this is a delocalization of sigma electron. So here what will happen, this is your X, this is your Y, and there this hydrogen is going to delocalize. So not the pi bonded electron will delocalize, the sigma bonded electron will delocalize, and ultimately we would be getting the structures like this part will remains the same. Here I am not going to do any change. So let's say this is HA, this is HB, and this is HC. Okay, so one time can happen that this HA is going to come and neutralize this carbon, and then we will be having HB, and this is HC with a positive charge. Or the another time can happen, the HB is going to resonate. When the HB is going to resonate, we will be getting, here we will be getting HB, and then the HA will remain as it is. We will be getting a positive charge, and HC will remain as it is. And if there would be a possibility that HC will resonate, HC will resonate. If HC will resonate, then what can happen? The neighboring is come to take care for you. HC will resonate, then HA will remain here, HB will remain here, and we will be getting a positive. So how many hyperconjugating structures we got? So here we got the first structure when we have replaced HA. Here we got when we have replaced HB, we got the second hyperconjugating structure, and when we have replaced HC, we got the third hyperconjugating structures. Okay, so as the number of alpha hydrogens we have, number of alpha hydrogens is directly proportional to the number of hyperconjugating structures. Number of hyperconjugating structures. Okay. And guys, more the number of hyperconjugating structures, more will be the stability. Means if you will be having so much of neighbors, those who are ready to help you, then definitely you will be having more stability, right? So yeah, I do have so many people around me. So whenever I will be getting into a situation, yeah, there is someone to help me. Okay, so yeah, if required, only the alpha, the nearest one can only going to help. the carbon with a positive charge. Okay, so this is a hyperconjugation. That is the delocalization of sigma bonded electron. That is the delocalization of sigma bonded electron. Here, is there any pi bonded electron who is getting delocalized? No, only the sigma. And this is also a property between the X and Y. Okay, so if you are talking about Mr. Member is saying, ma'am, 3-degree carbocations are more stable, so localization should be on left carbon. Absolutely, absolutely. So I'm not saying that this is a stable carbocation. I'm not teaching you the concept of a carbocation. I am saying that this particular carbon with a positive charge is stabilized because of the 3 alpha hydrogen. But if in case you will put a positive charge over this particular carbon, definitely it will be more stable. Why? If I will be putting a positive charge over this particular carbon, let me change the color so that there would be no confusion. Okay, this question is not about the stability of carbocation first. Okay, so whenever I will be talking about this particular carbon with a positive charge, then who will be the alpha? This will be the alpha, this will be the alpha, this will be the alpha, and this also will be the alpha. So for this carbon there are so many alphas, and over the alpha there will be so many hydrogens. So 3 hydrogen, 3 and 3, 6 and 3, 9 means 9 alpha hydrogens. So I told you, more the number of alpha hydrogens, more will be the hyperconjugating structures and more will be the stability. You please write, more will be the stability. Okay, will be the stability. Okay, so as the number of hyperconjugating structures we will be getting, they will be the carbon who is near to the carbon under consideration would be considered. Yes, absolutely, Kaushal. The carbon which is the nearest one. Okay, Acha, who is your neighbor? Neighbor's neighbor is your neighbor, or the neighbor is your neighbor? The one who is very close to you, the one who is sharing the boundary with you, is a neighbor, na? So this is what I am saying. Okay. Chalo. That's it, guys. So here in today's class we have focused over all the 4 methods in one single hour. Okay, so guys, let's have a look, okay, on a wider look. Let's have a wider look. So inductive is tug of war. You can say that pushing, pulling, pushing, pulling, pushing, pulling. Who will win the race? Okay, tug of war. And if I am talking about the resonance is a passing the blow. Okay, I'm passing my electrons one to another, one to another, one to another. This kind of passing the blow is happening. Now, another point that you have to focus. This is a property of this is a displacement. This is a displacement of electron. This is also a displacement of electron. This is also a displacement of electron. Okay, the inductive and the electromeric is a displacement of electron. Okay, displacement of electron through a sigma bond, This is the carbon family and this is your group. So the displacement of electron, where the electrons will get displaced here or there. Okay, and here we are having a displacement between the carbon and the group. There is a displacement of pi bonded electron. Are you getting? So here how many atoms we have used? 2, 2. Okay, now here we are saying that this is a delocalization. Now please focus. This is a delocalization. This is also a delocalization. Resonance and hyperconjugation is a delocalization of electron. So delocalization can happen in between how many atoms? Between 3 atoms. Okay. So here for the delocalization of pi electron. Okay. So this pi electron will get delocalized if here we will be having any positive, negative, lone pair, pi bond, or deficient orbital or something. Okay, then only the delocalization of electron will occur. This is a delocalization of sigma electron. Means I will be doing a delocalization but with no pi bond. Okay, so my X will do the delocalization with the hydrogen that I will be having over this Y. Okay, so with this alpha hydrogen. So this is your alpha and this is your hydrogen. So are they bonded with a pi bond? No, they are bonded with a sigma electron. So are you getting this in broader view? Okay. So which is a property of what? Okay, and whenever we will be having a question and there we have to apply all the properties, then please, we must prioritize. So whenever you have to apply the property in any of the question, okay, just let me give you an example. If I'm having a question like CH3, CH, double bond, C, and this is SO and H. Okay, if you would see here, you would say that, ma'am, I am having a pi bond. I can apply the electromeric effect. Okay, yeah, you are right. You can have the electromeric effect as well, because there is a pi bond. You can break the pi bond. You can do the displacement of pi electron. You would say that, ma'am, I'm having a sigma bond. This is a group and this is a carbon family. I can see that this is my sigma electron. I can see that where the displacement of electron will occur. Okay, you can also do the inductive effect. Okay, fine. You can have a look over the inductive effect. Fine. But at the same time, if I ask you कि okay बच्चे, you do let me know, here I'm having a pi bond, this is x double bond y, let me change the color. Okay, if I'm having x double bond y, this is single bond z, and here also I'm having a lone pair, then you would say, ma'am, here we can also do the resonance. Okay, so all the effects you will apply in one single question, or what you will do, right? Many of times we come in such a worse situation where we have all such things happening. Now another student would say ki ma'am, you tell me, okay, if this is this and this is the hydrogen, so can I do the alpha hydrogen? I can do the delocalization of sigma electron with this carbon. I can say that this is my x and this is my y. Okay, this is my sigma, and this over this y we are also having the hydrogen, which is the sigma hydrogen. That is for this particular functional group. This is my alpha, this is my alpha, and this is my alpha hydrogen, and this is my alpha and this is my alpha hydrogen. I can also do the hyperconjugation. So there could be a possibility that I could do everything there. I will try to do everything. Then what you will do? Guys, in such a case, always follow one concept. That is the prioritize. How you have to prioritize? You have to prioritize in such a way. That is A, E, R, H, I. I will be keep telling you about this. Okay, this is an important rule for the GOC. A, E, R, H, I. A is for aromatic, which I will teach you some another class. Okay, so here if you have E, okay, after A there comes E, so if you have E, so first of all we have to apply the electromeric effect. Okay, electromeric effect. But do we have any unsymmetrical reagent present to us? No. In this particular question there is no unsymmetrical reagent, no cation, no anion is given to us. So how we will be applying the electromeric effect? No possibility. So that is a breaking of this particular bond. Definitely when we do the resonance, we break this particular bond. Now there comes the resonance. So first, out of all this method, you have to apply the electromeric first and then the resonance. Inductive, hyperconjugation, no other method would be applied. Okay, so focus over, okay, yes, I have to break this particular bond. In which particular direction this bond will be broken? The electromeric effect will give you a sense ki, okay, this pi bond has to be broken. Displacement of pi bonded electron. Okay, the displacement of pi bonded electron should be in this particular direction. Okay, so temporarily this will become negative, this will become positive. Temporarily. Okay, we know that this is a temporary effector. Okay, temporary effector. And here then next the resonance, we can see that, okay, this is x double bond y single bond z. Over the z we have a lone pair of electron, so this lone pair will also go there. Ultimately what we will be doing is, we will be doing this kind of sign. This will become CH3, this will become CH negative. Here the single bond, we will be having C double bond OH positive, and this is going to be the resonating structure. Clear to everyone? So guys, this is it for today's class. I wanted to tell you about the difference between all the things. If you would just focus over the definitions, which is a sigma bonded, which is a effect of a sigma bond, which is the effect of a double bond, which is the effect of a when the 3 atoms are required, when the 4 atoms are required. Okay, so always remember, here we required only, this is a property between the 2 atoms. Only the 2 atoms we have to focus. Here also we have to focus over the 2 atoms. Here we have to focus over the 3 atoms, X, Y and Z. And here again we have to focus over the X, Y and hydrogen. That is these 3 atoms. Okay, so this is it. I hope you understood today's lecture. Not necessarily caution that the third carbon for the hyperconjugation has to be a carbocation. In which question you are saying? Kaushal, we will not be, it's a temporary effect. We can't put a positive charge over there. Okay. From the electronic displacement method, we can predict that, okay, yes, this pi bond has to be broken. Okay. So the pi bond has to be broken first, but then after the oxygen will be giving its electron pair, and so therefore this will become a double bonded electron. The negative charge will come over there and the positive charge will come over the oxygen atom, not over the carbon. Okay. No, partial third should not be a carbocation. Because here the resonance is happening, not the electromeric is happening. Electromeric effect is a temporary effect. Okay, so if you will be having any of the unsymmetrical reagent, then we will break a bond and will do the reaction. We can do the any kind of addition reaction, that is the electrophilic addition could occur. Okay. Chale guys, it's good to see you all there. If you have any doubt related to this, do let me know in the comment section. If you are liking this, please do let me know. Okay, so it's a very simple thing. Just focus over the definitions that you are having and just related with the games which I tried to focus over. So keep learning guys. Here I will be coming up with the next videos that will be on the resonance stability and the resonance in the aromatic compounds, so that we will be focusing over the more of plus m and the plus I plus minus m effect. Okay, so more such videos are going to come. We will also be having a focus over the carbocation and its stability. Just a minute, Kaushal is saying something. Ma'am, kindly look where the 4 bonds of that third carbon. Array 4 bonds, the other is going to be the hydrogen. I have not shown that. It's as simple as that. Okay, Kaushal. This is going to be the hydrogen atom. It has, write it as CHOH. 1, 2, 3, 4. Of course, there will be 4 bonds. So write it as CHOH. Oh my god. So this is what he was trying to tell me. Just complete the valency of the carbon. This is going to be CH double bond OH. Now is it fine, bache? Sometimes this goes wrong. It's fine now. Now every carbon is like completely balanced. Is it clear now? Kaushal, just give a hand raise if everything is fine now. No. There should not be a carbocation. I was not tend to put a positive charge there. I was just telling you that this pi bond, if broken, will be negative or positive temporarily. Temporarily. This should not be a positive charge. No. Here I have to put hydrogen. I just missed that. Okay, fine. Okay, thank you so much guys. So this is it for today's session. Thank you. Please like and subscribe for the channel, and if these sessions are helping you, please do let us know what else you want to learn and what you people are like looking for. And we have started this particular channel to help our learners to achieve their dream. So this is now an academy has a dream to democratize the education. Whosoever across the country, whosoever remotely, if they are learning, then they could be able to learn freely. Okay, the quality education could be imparted to every student. Okay, no, irrespective of where you people are learning from. So this is it guys. Thank you so much. You can also follow me on an academy. There are so many plus courses which I am taking live. Okay, just a click away. You do follow me. As you can see, there are 127,000 plus students who are learning from my courses. And I have also got the People's Choice Award over the Unacademy, and I am now All India rank 25 in CSI UGC net. Okay, so for the chemistry, you people could rely on me and just go the way I am teaching you. Slowly and steadily you will be able to understand all the concepts, the basic concepts which I am going to take in this particular channel. Thank you guys. See you all there. Bye bye. Take care.